Hello, this is video 35. The saga of the red-black tree questions and answers continues. We are up to, I think, question number 5. The split, remember that's what we did on the way down, and we've already discussed that. What about the rotate when the tree is unbalanced because it's got 2 in a row, either in a straight line or in the crooked line? 5, how do we rotate? And that is the word that's used. An unbalanced mini tree inside a red box. You know what? I'm just going to call it an unbalanced mini tree. Mini tree implies that it's inside the red box, and our secret is out now. The red boxes don't even really exist, but it's still very useful to view it in those terms. So when we refer back to the pictures that we drew so that we could write our program, then we've got an intuitive frame of reference. When do we do this? When? That's all question. A multi-part question. Answer. Well, again, the when part's easier, I think. When we are on the way back up the tree at the end of the put function. Now, that almost answers the footnote I did on the last one. Well, when do we rotate an unbalanced mini tree? When we are on the way back up the tree at the end of the put function, well, not in all cases, at the end of the put function, comma, whenever we detect, what is it we're going to look for? An unbalanced mini tree is going to be exactly 2 red nodes in a row. And again, if we've done everything correct up to this point, there can't be 3 red nodes in a row, or 4, or 5, or anything bad like that. Our worst case that we have to deal with is 2 red nodes in a row. And you'll notice I didn't say 2 red nodes in a straight line, or 2 red nodes crooked one way, or 2 red nodes crooked the other way. Doesn't matter. Any of those, we're going to have to balance them. Whenever we detect 2 red nodes in a row, I'm going to slip in some non-technical terms here. Behind us. I almost felt like putting that in quotes, but I don't think I will. When we are on the way back up the tree, asterisk, after, that's going to be after the recursive calls. That's when we're coming out of the recursion on our way back up to the public wrapper that's going to take us back up to the main program. After the recursive calls to put, now then, can I finish the sentence? When we are on the way back up the tree, which will be at the end of the put function, whenever we detect 2 red nodes in a row behind us. I don't know that I can put a double asterisk footnote on that to explain it any better. But what? How do we rotate? Well, I could do that. I'll do that almost as an aside here. This will be question 5a. How do we detect that? How do we detect 2 red nodes in a row? Maybe that's just so simple it goes without saying, but we can say it anyway. How do we detect 2 nodes in a row, 2 red nodes in a row? Maybe there's a fancy way. I don't know of a really fancy way. I would say just stop and turn around and look behind you and see what you got. A miniature, this is a question 5a. A mini exhaustive search. In other words, just look at all the possibilities and see if any of those fit the bill. Exhaustive, E-X-H-A-U-S-T-I-V-E, search. A mini. I'm going to put mini up front. Otherwise, exhaustive search, that implies order in. You got to look at everything one at a time. 1, 2, 3, 4, 5. Yeah, we don't want to do that. Except there are only 4 possibilities. Exhaustive search, left. No, let's see. I'm going to write that differently. Left child and left arrow left child. I like that better. Are read. There. Possibility number 1. I'm going to do ditto marks. Left child and ditto ditto. Left arrow right. That's another possibility. That's the crooked case. If those are both red, I'll put red again. There. And wait, there's 2 more. Right. The right child and the right arrow left. And it doesn't matter what order it is. You can put them in any order you want. I'm just trying to keep up with what I've done and what I haven't done, which is why I'm doing them in this order. Right and right arrow left children are both red. 1 more. The right child and the right child. Right child and right arrow right child. Child are both red. Quick test. Exhaustive search just means you look at all 4 of them. You don't necessarily have to look at all 4 of them. They're mutually exclusive. Yeah, that's easy for me to say. If we run into this one, for example, left arrow right, if that's a crooked 2-node little path of red nodes, then we don't have to look at the other 2 because they're not possible. Only one of these could be possible at a time. So once we find one, we don't have to keep looking. So it's an exhaustive search until we find one, or we don't find one. There's not any guarantee that we will find any of these. Now, sort of in this, let me be very careful here. Look at this, we're dereferencing the left pointer. There's actually more testing going on than you see right here in front of you. First of all, there might not be a left child. The left child could be 0. So if that's true, and we try this, then we got the problem. The left child has to exist before we check for left. So there's all kind of testing we'd have to do. We'd have to check to see if the left child exists. Oh, it does. Then let's check the left arrow color of it, or left arrow is red, however we're representing color. Then we're still on this line. That was 2 tests already. Does the left child exist? Is it red? Then we check to see if the left child exists, and is it red? So even though this looks fairly straightforward and simple, or at least perhaps it does, this one line right here is going to require at least those 4 tests. Does the left child exist? There's 1. Is it red? There's 2. Is the left child exist? There's 3. Is the left child red? There's 4. If all 4 of those are true, then this, we don't even have to look at the other 3. This is the one we're going to have to deal with. This is the one we're going to have to use to do the rotation. Okay, and similar discussion for all the rest of those. This is me hand waving. Similar discussion for all the rest of those. Ditto, ditto, ditto. But if you understood the left case, then you should be able to get the rest of them there. It's easy for me to say, huh? How do we rotate it? That'll be my 5B question. How do we rotate an unbalanced mini-tree? My answer is how indeed. How's that for an answer? That's going to have to be another video, because that is probably just the answer to that one question. How do we rotate an unbalanced mini-tree? That's going to take up the board several times. Each one of these requires its own special type of tree surgery to rebalance the little mini-tree inside the non-existent red box. So this is a loaded question here. How do we rotate an unbalanced mini-tree? just toss that out there as if it's going to be a simple answer. It is not a simple answer. It's a messy answer, and I'm sorry I scared you. Watch the other video, the next video, and everything will be fine. I'll see you online.